Hello, here we are going to continue with alpha and beta. So we decided to see that we have seen that the sum of roots of an equation, of a quadratic equation, alpha plus beta is given as negative b all over a. And the product of roots is given as c all over a. So now the question we need to ask ourselves is, in this equation, 2x squared plus 3x minus 1 equals to 0. In this equation, we see that c alpha plus beta is equals to negative b is 3 all over 2. So this is our alpha plus beta. And alpha beta is equals to negative 1, which is c all over 2. Now, if you are asked to find for alpha minus beta, what do we do? Alpha minus beta is equals to the square root of alpha minus beta all squared. So this is a simple method of calculating alpha minus beta. We do the square root of alpha minus beta all squared. So alpha minus beta all squared is equals to alpha squared minus 2 alpha beta plus beta squared. Now, when we have this, it's equals to alpha squared plus beta squared minus 2 alpha beta. And now, we should note that there is a method for us to calculate alpha plus beta all squared. Now, this method of calculating alpha plus beta all squared is equals to alpha plus beta all into squared minus 2 alpha beta. Because this, if we expand this, we are going to have this. Let's see it. So it implies that we are going to have alpha squared plus 2 alpha beta using the right hand side of the equation. Alpha beta plus beta squared minus 2 alpha beta. 2 alpha beta minus 2 alpha beta is going to give you 0. So we are going to alpha squared plus beta squared. So alpha squared plus beta squared is equals to alpha plus beta all into squared minus 2 alpha beta. So when I substitute it back in this equation, so I'm going to have alpha minus beta all into squared is equals to this. I substitute this into this. So it's going to give me alpha plus beta all squared minus 2 alpha beta. Now, I initially had alpha beta here. I substituted back to alpha beta. So my alpha minus beta all into squared is equals to alpha plus beta all into squared minus 2 alpha beta minus 2 alpha beta is 4 alpha beta. I can now substitute back. So if I'm asked to calculate for alpha minus beta, we said alpha minus beta is the square root of alpha minus beta all that squared. So I find first alpha minus beta all that squared. Alpha minus beta all that squared is given by alpha plus beta all squared minus 4 alpha beta. Now alpha plus beta, we've calculated it to be negative 3 all over 2. We substitute it back, negative 3 all over 2 all into squared minus 4 into alpha beta. Alpha beta is negative 1 all over 2. Negative 1 all over 2. So alpha minus beta all that squared is equals to negative 3 squared is 9 all over 4 minus 4 into negative 1. We can cancel the negative and we have a positive sign outside. Put the 2 outside, so we have 2 here. So alpha minus beta all that squared is equals to 9 all over 4 plus 2 all over 1. Now we are going to find the lowest common multiple. Alpha minus beta all that squared is equals to, we have 4 here. This is 9 plus 4 times here. It gives 4. 4 times here, it gives 8. So alpha minus beta all that squared is equals to 17 all over 4. So alpha minus beta is going to be the square root. Now we have to note that the answer of alpha minus beta can either be a plus or a minus. Don't forget. Now, the question is why So you see that alpha minus beta, you are going to have two values of alpha minus beta. The reason here is because you are capable of permutating alpha and beta. Now, let's say alpha is 2 and beta is 5. We see that when you have alpha 2 and beta is 5, alpha minus beta is not the same as when you do addition. Let's say 2 plus 3, 2 plus 3 is always going to give 5, so 5 is associative. When you add 2 plus 3 and invert the position, if you add 2 plus 3 and invert the position of 2 and 3, they are all going to be equal to 5. But the alpha, when you subtract 2 minus 3, it's not equals to 3 minus 2, which is not equals to, always equals to the value you are finding. So alpha minus beta has two values, while alpha plus beta has only one. Because addition is commutative, it's capable of permutating, you're capable of permutating the position of the numbers. So now here you're going to have a plus or minus. So your alpha minus beta is going to be plus or minus the square root of 17 all over 2. Alpha minus beta is equal to plus or minus the square root of 17 all over 2. Again, the last part of our equation in alpha and beta is alpha cube plus beta cube and alpha cube minus beta cube. Alpha plus beta cube is given as alpha plus beta all into alpha squared minus alpha beta plus beta squared. And alpha minus beta is alpha minus beta into alpha squared plus alpha beta plus beta squared. Here you have already defined the alpha minus beta, and we already know alpha squared plus beta squared, and we can calculate for alpha cube plus beta cube and alpha cube minus beta cube. Now the question is, how do we prove these two formulas? Now for me to prove these two formulas, I will let the equation f of x equals to x cubed plus a cubed. This equation is a polynomial. Now, we know from the remainder theorem in polynomials, that if I substitute the value of x inside here and the remainder is 0, it implies that that value I've substituted is a root. If I divide this polynomial by a certain linear equation or linear function, and I have a remainder which is 0, it implies that that linear function I've divided with is a factor of the polynomial. Now, by the remainder theorem, if we reach, what can I substitute here to have f of x equals to 0? So for f of x to be equals to 0, it implies that x cubed plus a cubed is equals to 0. So x cubed is equals to negative a cubed. Now, if I remove the cube on both sides, I'll see that x will be equals to negative a. So I can substitute negative a to have here. When I substitute negative a here, I'm going to have a 0. So x equals to negative a. When I substitute negative a here, I'm going to have this. So the factor will be x plus a equals to 0. So the factor of this equation is x plus a. So if I divide this equation by x plus a, the equation is x cubed. Now I'll add on some other variables as 0. So if I do 0x squared, I didn't change anything. If I do 0x, I didn't change anything. Plus the last one, which is a cubed. Now let's start dividing. I divide here, x cubed divided by x, it gives me x squared. So here is x squared. I multiply here by x, it gives me x cubed. I multiply here plus ax squared. Now I subtract, I have 0 here, and here I have negative a squared. I add here plus a 0. I do negative a squared, I divide, it gives me negative a x. I multiply here, it gives me negative a x squared. I multiply here, it gives me negative a squared x. I subtract. When I subtract, I'm going to have an addition here. So I'm going to have ax squared plus a cube. When I multiply here, I see that when I divide here, I'm going to have plus a squared. I multiply a squared x and I multiply here plus a cube. When I subtract, the value here about 0. So it shows me that the remainder at this point is 0, and truly that x plus a is a factor of the equation x cubed plus a cube. Now, I have factorized the equation x cubed plus a cube, x cubed plus a cube as being equal to x plus a all into x squared minus ax plus a cube. Now, I can do the same and compare it with this one. If I say that x is equal to alpha and a is equal to beta, then comparing them, I see that x cube plus a cube is equal to x plus a into x squared minus ax plus a cube. And now, in this case, I said x equals to alpha, so alpha cube plus a equals to beta, beta cube. When I compare that, it's going to give alpha plus beta all into alpha squared minus alpha beta plus beta squared. So it ends up by having this same one here. If you do again with the other one, which is x cube minus a cube, here in this case you're going to use a factor which is the contrary of the other factor we had here, x plus a. The factor in this case will be x minus a. You continue again by dividing here with x cube plus 0x squared plus 0x minus a cube, and when you divide, you're going to have a value as such here. So this is how to prove the different forms of x cube plus b cube and alpha cube plus beta cube and alpha cube minus beta cube. So the next section we are going to see right now will be the turning points. We can find the turning point in two ways. The first way is by the way of differentiation. The way of differentiation is quite easy, but we are going to use long step of differentiation in order for us to have our turning point. So the way here is just as such. You have the initial equation, you have f of x, a quadratic function as being ax squared plus bx plus c. And here, in order for us to have a turning point while using the method of differentiation, the way is by doing so that f prime of x will be the gradient function. The gradient function, you know that you're going to have 2ax, the formula for differentiation of y with respect to x, or when y is equals to x to the power n will be equals to xn minus 1 times n here. So when I do the f prime of x, so the f prime of x differentiation, I will multiply here is equal to 2ax plus I multiply here and I subtract the power of x by 1, so it gives me b here. So this is the gradient function of a quadratic function. Now, when I have this gradient function, I can then ask myself the question, see that this gradient function is linear. Now, how do I do to find the turning point when I have the gradient function? We know that in a graph, quadratic graph, the quadratic graph can have either a maximum turning point if a is less than 0, or it can have a minimum turning point if a is greater than 0. Now, we have to note something. At the turning point at this maximum or minimum value, if I draw a tangent at this portion here and at this portion here, I see that the gradient at these both points are going to be 0. So we can easily give an assumption that at the turning point, the gradient is equal to 0. So you will say that f prime of x will be equal to 2ax plus b. Now, at the turning point, you know that at turning point, the gradient is equal to 0. So it implies that the f prime of x will be equal to 0. So we are required to find for the value of x when the f prime of x equals to 0. I'm going to do 2ax plus b is equal to 0. So it implies that x is equal to negative b all over 2a. So we have calculated the corresponding value of x when at the turning point, and this will correspond to a symmetry, because when you see in curve sketching of quadratic equation, when a quadratic equation have either a maximum or a minimum turning point, it will have a point of symmetry which will divide the two portions of the graph, the left side and the right side. This line here is x equals to negative b over 2a. Now, to find the corresponding y on this line, how do we do? I take this x and I substitute my initial quadratic function. The initial quadratic function f of x is giving us ax squared plus bx plus c. When I substitute this in this equation, I'm going to have f of negative b over 2a is equals to y at the turning point. So the y at the turning point is equal to a into negative b all over 2a squared plus b into negative b all over 2a plus c. Now, I do is equal to a into b squared. I square this all over 4a squared plus negative b squared all over 2a plus c. I continue up here and I have b squared, a will cancel here. So it's going to give me all over 4a minus b squared all over 2a plus c. And now find the lowest common multiple. The lowest common multiple will be 4a. I have b squared minus, I do here 2b squared plus 4ac. So my y at the turning point will be equal to this b squared minus 2b squared is negative b squared. So it gives me 4ac minus b squared all over 4a. So my y at turning point will be this. So I say that turning point, let's say the turning point P will be represented with an xy coordinate of P being negative 2, negative b all over 2a and 4ac minus b squared all over 4a. So this is the method 1 for us to find the turning point using a quadratic equation. The method 1 is a general method which can be used everywhere for us to find the turning point. But it's a particular method which is used in case of quadratic functions. Another particular method is by completing the square. So method 2. We are going to complete the square now in order for us to find the turning point. These 2 points here. We still have the same function y is equal to ax squared plus bx plus c. Now, by completing the square method, we initially set that y is equal to, in this case, we are going to factorize a as such. So when I factorize a, I'm going to have x squared plus bx all over a plus c all over a. Because I can't put a on this side because y is not 0. In other case of completing the square, we just divide it all around, and when it arrives on the other side of the equation, it finds 0. 0 divided by any number gives 0. That's why we initially didn't have the a as such, but here we have to factorize, because when I'm going to divide, I'm going to have y over a. I don't want the a to find on the left hand side of the equation. So y is equals to a. I put this curly bracket, and now completing the square, you maintain the x, you maintain the sign, you take the coefficient, you divide it by 2, b all over 2a, you put it all squared, minus, you take the coefficient that you initially found, b all over 2a, you put that coefficient squared plus c all over a, and then you close your bracket. So the y here is equals to a all into x minus b all over 2a squared minus b squared all over 4a squared plus c all over a. So y is equals to a bracket x minus b all over 2a squared minus b squared all over 4a squared plus c all over a. Now we are going to find the lowest common multiple here. So you have ax plus this. So find the lowest common multiple of this. So I have y is equals to a into x minus b all over 2a squared. I do a positive side here to incorporate all this inside. So I have 4a squared minus b squared plus 4ac. Now I'm going, you have y is equals to, then you have this, I put the bracket inside. I have this like this. When I put also inside in this other position, I'm going to have 4ac minus b squared all over, when I put, I'm going to multiply, I'm going to have 4a. So I'm going to realize that this one, which on this side here, is going to correspond for the x coordinate in the maximum turning point. So when you see that I put x is equals to negative b all over 2a, when I put this x negative b minus negative b over 2 equals to 0, I'll have x equals to negative b over 2a. And this corresponding point here is a y position at the maximum turning point. So that y position maximum turning point is 4ac minus b squared all over 4a. And this is the same as what we found initially. So at the turning point, you have negative b all over 2a and 4ac minus b squared all over 4a. So these are the values that you find at the level of the turning point. Thanks for your kind attention.